Okay, today we're going to talk about the Bidual and the reflexive spaces. So remember that we showed it before. So if I have a B star space or a normal linear space, then the X star, which is the set of linear functionals on X, forms a Banach space using the operator or functional norm. Right. So this is the B space, Banach space. So because this is the Banach space, we can further consider the dual space of this. So in that case, we'll have X double star. Okay, and this is the set of linear functionals defined on that. Okay, and this is called a Bidual. Okay, this is called a Bidual. Okay, and then you can also define the norm similarly as before. Define the operator norm in this, and that would be also a Banach space. Okay, so what is the relation between this Bidual and the original X? Well, let's think about a simple mapping between the two. For example, for any X, let's consider this mapping. For any point X, we can define a linear functional Jx. So this Jx is in here. So that means the Jx is a bounded linear mapping from X star to R. Okay, so Jx itself is a bounded linear mapping from X star to R. So that means for any element f in X star, so this f is a bounded linear functional on X, it will be mapped to the Jx of f. And how we define this Jx? It is defined as the function f evaluated at this x. So once we choose this x, we can just directly get this Jx as a mapping from X star to R, and it is simply taking any bounded linear functional f in X star and evaluate at the point X. So this is probably the simplest kind of mapping from this X to X star, X double star. So for every X in here, we know that there exists such a mapping or such an element in the X double star or the Bidual such that it holds. Okay. So one more thing that we can notice is that we look at the Jx of f. By our definition, it's just the f of x. Okay, and as you can see, this is bounded by the functional norm of f times the norm of x. Okay, and this is true for any f and any x. Right, this is true for any f in X star and also any x in the space X. And this implies that the Jx as a mapping in the Bidual or as an element in the Bidual has a norm less than or equal to x, right? Because it's like for any Jx, this is bounded by the norm of f itself times some constant. So that means the norm of Jx must be less than or equal to this constant, which is x. Okay. So now this gives us a very simple mapping from x to X star, and we call it the T. So T is just mapping x to this Jx. And this T is called canonical mapping. So I this T here called canonical mapping. Sometimes it's also called evaluation mapping. Okay, so that means the T just maps this x to evaluation. So that means Jx is the evaluation for any given f, just evaluate this f at the point x. Okay, so that's the common name for the t. And we can easily show that this t from x to x double star is a linear mapping. Okay. Or it's a linear operator. And the reason is, as you can see, we just need to verify that t of, say, alpha x plus beta y. So the x, y, they're from the space x. Alpha and beta are any real number. Let's see if this is equal to the alpha of tx plus beta times ty. Right, that's what we need to show. We want to show it is linear. We want to show this. Remember that this gives us a mapping. This is the mapping in x double star, right? So this is in x double star, or in the Bidual. So in the Bidual, how do we show that this Bidual is what this Bidual is? We just need to evaluate it at any element in x star in the dual space, such that it is equal to. So I shouldn't erase that one earlier. So I need to check this on f, and I want to show that it's the same as I'm doing this. Okay? If this is true, this is true for any f. For any f in x star, then we show that this operator and this operator right here are equal. Okay, so that's what we need to show. Okay, that's our goal. Just keep it there. Okay, so by definition, the t maps this element to the evaluation j. So that's just the j of alpha x plus beta y. Just treat alpha x plus beta y as one element in x. Okay, and I evaluate that f. And as we know, this is just applying f or evaluating f at the point alpha x plus beta y. But because f is in x star, so it's linear. So I have f alpha times fx plus beta times fy. Okay, and as you can see, this is just equal to alpha times the jx at f plus beta times jy at f. Okay, but remember that jx and jy, they're all linear mappings, right? They're all linear functionals. Jx, jy, they're from x double star. So they're linear functionals defined on x star. So that's why this is just alpha jx plus beta jy. And then we need to apply to f. Okay, but the jx and the jy, they're just t of x. Right? They're just t of x, the t and t of y. So just evaluating this to f. And that is exactly the right hand side we wanted right here. Okay, this implies that t is actually linear. Okay, and also not just linear, it's also bounded. The reason is we'll look at we actually showed this before. When you look at the tx, right, for any x, the tx is equal to the jx, right? That's what we got, and this is less than or equal to x, as we showed before. So for any fixed x, the tx, the norm of tx, is actually bounded about by the norm of x, and this implies that t is a bounded linear operator, or is continuous linear operator from x to x star, x double star, okay, from x to the Bidual. Okay, so actually we can show that this inequality is just a big equality. We can actually show these two are equal. Okay, to show that, let's look at. We just need to show that the tx is just equal to the norm of x. To show this, let's say for any x in space x and any f in the dual space, well, we should say this. For any x in the space x, we know there exists some f in the dual space such that the norm of f is equal to 1, and also the f of x is equal to norm of x, right? The reason is, let's say we can, to show this, let's say we can consider some f naught. Let's define the x naught first. So let's define a linear subspace x naught to be just some linear multiple of x naught over this x. Sorry. So the x is this x here, so it's fixed, and this a is any real number. So I know this is space x naught. It's a linear subspace of the true x, of the original x. And I can also define linear mapping, say f naught, so from x naught to r by, so I know that every element in the space, linear subspace x naught, can be written in ax. So I'm going to define this to be a. Okay, or maybe a norm of a. The a times the norm of x. So it's just a constant right now. The norm of x is just a constant, doesn't matter. So I can do this. Okay, and then by doing this, you can see the f naught. So the f naught has the norm equal to 1, right? Because the f naught of ax, so we show that it is equal to a times that. Okay, and this is equal to the ax norm. Okay, so the norm of f naught is just equal to 1. And also, f naught is bounded above by this quantity here. So it's bounded by, so I define px to be the norm of x. So I'll see that the f of this x is for any x in the space. So let's say py less than equal to y. Y is from this whole space x. So you can see that this is bounded by px, bounded about by this linear sublinear functional, which is just the norm. Okay, and then by Hambana Theorem, we know that we can extend this f naught from the space x naught to the whole space x. So we can use the Hambana Theorem, we can extend the f naught from x naught to the whole space x, such that the extension we call it f, and when we restrict that to the f to the linear subspace, we just get the f naught. And most importantly, we know that this f has the same norm as that, which is equal to 1 right now. Okay, and also it takes the same value as f naught. So when we evaluate f at this particular point right here, it should be equal to f naught of this x, which is just the x itself. Sorry, just the norm of x right here. Okay, so that's how we got made that claim. Okay, this is how I made that claim. Okay, so because of this, we know that I found this particular f, and let's apply this jx to this particular x. What happens is, we look at the norm of f. We know that this is equal to fx, right? This is how we got this f right here. And then this is the less than equal to, sorry, this should be equal to the jx evaluated f. And that is, jx is just the tx evaluated at f. Okay? And according to, this is just less than equal to, remember that this thing here is in x double star in the bidual, and this f is in the dual space. So this is less than equal to the Tx norm. The norm is in the Bidual. And then the norm of f, which is the norm in the dual space. And then we have that. Okay, and this f here is equal to 1. So that's why I just have the Tx. Okay, so on the one hand, we show that Tx is less than equal to the norm. The norm of Tx is less than the norm of x. And on the other hand, we show that, which is also less than this. So that's why the two are actually equal. So the Tx is just equal to the norm of x for any x. Okay, so what this means, remember that T is a mapping from x to the Bidual. And it maps every x to the Tx. Okay, and what we have shown is that the norm is kept. So that's why the T is actually isometric isomorphism. Okay, or T is isometrically isomorphic from x to the Bidual, x double star. Okay. And moreover, so in this case, you can imagine that this x double star is generally larger than this x because this seems to be a subset of the Bidual. And also this can be isometrically embedded into the Bidual since the norm is kept. Okay. But remember, this is the Banach space, and this could be a B star space, which may not be complete. But if it is complete, if this one is also complete, which is also B star, and this is also B, this is a B space, this is also B space, then we're actually making a isometric embedding from this X to a subspace of that, which is also closed, because this is closed. It's embedded in there is also a closed subspace. Okay, closed linear subspace. So when the X is also Banach space, the embedding is we're going to get a the embedding of X into this Bidual is a closed linear subspace. Okay, so I summarize the result right here. It's isometrically isomorphic. To a closed linear subspace of the Bidual. Okay. So yeah, and in this case, you basically can think this X. You can identify X and the JX because of the X and the JX, which is just the T of X. You can identify these two because this and this are actually the same thing, right? They can both be applied to F in X star, and the difference is the JX of F. It's always just equal to the F of X. So sometimes when we write it, it's easy to write it as like f of fx. This is not the inner product in a Hilbert space or inner product space. What this means is that this is in X, and this is in X star, and we can always write this as dxf, where this x should be interpreted as jx or tx, because this is in X double star. It's in the Bidual, and this is in dual. Okay, so whichever goes first in this inner product notation, or in this bracket, means that this is the one that is applied to this second one. Okay, so that's the interpretation. As I said, in general, this X is embedded in this Bidual. But if this X is actually the same as the Bidual, we call this X, reflexive. Okay, or in other words, we know that this means that T as a mapping from X to X double star is surjective. Okay, that means every element in the Bidual can be mapped from some element in X, in the space X, or any element in the X double star in the Bidual can be written in this way. Okay, so in that case, we call the space reflexive. And then, once it's reflexive, you can just, no matter how many times you apply the star, you always get back to, for the even numbers, you always get back to the origin X. So this is equal to that. And then when this is also equal to this, so on and so forth. Okay, so if that's the Bidual, it's a reflexive space. Otherwise, it may not be true. So example is, say if P is between 1, it's strictly greater than 1, less than, but finite, then we know that the dual space of this is LQ. But in this case, Q is also strictly greater than 1 and finite. So that LQ will take the dual, that will be just the LP. And in this case, you can see that the LP space is reflexive because we have that. Okay, if P is equal to 1 or infinity, then this is not true. So for example, when P is equal to 1, we know that the dual space of L1 is L infinity, but the dual space of L infinity is not L1. Okay, it's a set of measures. We call this. It's a set of measures such that nu is bounded, finitely additive, and also absolute continuous with respect to mu. Okay. So I will not expand on this anymore, but the idea is that for P is strictly greater than 1, we have a reflexive space. If P is equal to 1 or P is equal to infinity, then that's not. Okay. So that's one example. Now let's consider an important concept called the adjoint operator. Okay, and that is an extension or generalization of transpose of matrices. The matrices are really simple, right? You can think of them as linear operators from a finite dimensional space to another finite dimensional space. The transpose has a clear meaning, that is mapping back. But for finite space, what that means. So let me give you the definition. So let X and Y be Banach space, or in general could be even B star spaces. And T is a bounded linear operator, bounded linear mapping from X to Y. Okay, then let me define the adjoint operator. So the T's, then the T star as a mapping from Y star, the dual space of Y, to the dual space of X is called an adjoint operator if the T star of F, okay, T star of F, F is, as you can see, F is in the Y star. So after the mapping, it become, should say, it become element in the X star, right? So the F here is in this. The T star of F is in here. So it can be applied to any element in X. And we'll get a scalar, right? We'll get a real number. And if this is always equal to F of Tx for any X in the space X, and any F in Y star, then we call it a Adjoint operator. Okay. You can also think in this way, as we showed before. This can be written as in this way on the left-hand side, right? It's like you're applying this, which is in X star, to some element in X. And on the right-hand side, you can think this is as applying F to Tx, where this F is in Y star, this Tx is in Y. Okay? If these two are always equal for any X in the F, then we call this T star the adjoint operator of T. Adjoint operator of T. Okay, so from this notation, you can imagine why we call it adjoint operator. If you have this as a matrix, this as vectors, then the T star is like the transpose of T. Okay. So let's see that when T is, if this T star is well defined, meaning that if we can actually have such a T star as a mapping. So to see this, let's look at the T itself. For any T, and for any given T, and then we look at any F in Y star, what happens is we can define this GF. So this GF is obtained by determined by this F. And we can think it as a mapping from X to R. And we define to be the GF of X is just F of Tx. Okay? We just define the GF of X as F of Tx. Then it is easy to see that the GF is linear, because when we look at the GF of, say, alpha x plus alpha prime x prime, x and x prime are elements in X, alpha and alpha prime are real numbers, then on the one hand, according to the definition, this is equal to f of t of alpha x plus alpha prime x prime, right? And then this is equal to f of alpha t. I can even just remove the alpha outside. The alpha is f of tx plus alpha prime f of tx prime. And then you can see this is just the alpha of gf of x plus alpha prime of gf of x prime. So the gf is actually a linear mapping defined in this way. We define this that way. It's a linear. So that means, and also it is easy to show that the gf of x, according to our definition of gf, this is equal to f of tx, right? So that means it's less than equal to the functional norm of f times the operator norm of t times the norm of x. Okay? So that means the norm of gf is bounded by this quantity, which is finite, because t is a bounded linear operator and f is a bounded linear functional. That's why the gf is actually a bounded linear, sorry, it's just in the, it's bounded linear functional, it's just in X star. Okay, so for any given t and for any f, we can just define the gf in this way. So this is how actually we define the adjoint operator. We define the T star as a mapping from Y star to X star. So the Y star is, for any F, we actually map it to the GF. And this is how we define the T star. This is how we denote by T star of F. Okay, so it is indeed in X star. Okay. And also, let's look at the T star. It's pretty easy to show that T star is linear. As you can see, if you have, say, alpha F plus alpha prime F prime, it can be easily shown that it's just mapped to alpha T star F plus alpha prime T star of F prime. Okay, F and F prime are two functions in Y star, two elements in Y star. Okay, so it's linear, and also we look at this applied to F. We know that this is just a GF, right? And GF, as we showed, is less than or equal to the norm of F times the norm of T, and this implies that the T star is actually bounded by the norm of T. Okay, and actually we can still show the other direction. This is actually also true. But now at least we see that the T star is in L, Y star, X star. It's a bounded linear operator from the Y star to X star. Okay, so let me summarize the result below. One thing is that, say, let's define a mapping star. It is mapping any bounded linear function from X to T or to Y to any bounded linear operator from Y star to X star. By once I have that, so you know this is something. The elements in the LXY is the T's. They will be mapped to star T, which is in here, and this star T is just the adjoint operator. Okay, so the X star is just mapping any operator to its the adjoint operator. Okay, and also we should be able to show that this mapping star is an isometric isomorphism, and so this is a linear. I should say this. It's linear. I mean this mapping is linear, and isometric isomorphism. So linearity is clear. What I mean by that is just I want to show that when I apply this star to any linear combination in this space, I will get the linearity, which is, let's see, in this way. I have that, and because this after the mapping, it is somewhere here, right? It's something in here. Oh, sorry, some element in here. So this means that this can be. This means that this thing can map any element in Y star to some element in X star. Okay, so that means if I apply this, so remember that this is in L, Y star, X star. So when I apply this to F, which is in Y star, I will get something in X star. And once it's something in X star, I can apply it to X, which is in X. And the question is if we have the linearity from here. And the proof is straightforward, just do some computation. using by following the definition. So the mapping, as we said, the star mapping, here just mapping element operator to is the adjoint operator. So the adjoint operator is this: alpha 1 T1 plus alpha 2 T2 as a whole applied to F, and then applied to X. But the definition for adjoint operator here is that this is equal to F of alpha 1 T1 plus alpha 2 T2 applied to X, right? And then you can apply the linearity of F and T. So you have this alpha 1 F of T1X plus alpha 2 F of T2X. And the first one is just, by definition, it's just alpha 1 times the T1 star applied to F, then X, plus alpha 2 times T2 star, adjoint operator of T2, applied to X. And then from here, you can see this is just alpha 1, because the T1 star is a linear mapping, the T2 star is linear mapping. So we can put, if they are both mappings from the Y star to X star, so I can make a linear combination of them. Right? Apply to F. Okay, apply this to F, and then this to X. Okay, and this also means that this is just a alpha 1 of star T1, because the adjoint operator is just a mapping from, using star mapping from T1 to the T1 star. And also this is T2, alpha 2 star T2. And this apply to F, and then apply to X. And because this is true for any Y star and X, we know, so this is true for any F in Y star and any X in X. We know this just means that the two mappings are identical. So this mapping and this mapping, these two are actually the same. Okay, and this means that it's linear. The other thing is that we want to show is isomorphic, isometric isomorphism. So we already showed that this X star is mapping from T LXY to LY star X star, and it's mapping any T to its adjoint operator, which is this. So we know that this thing here is equal to the norm of the adjoint operator. We know that this is less than or equal to T. So I know this one, this direction. But on the other direction, we think about, let's say for any X, right below, for any X in the space, and Tx, say if Tx is not equal to 0. So remember Tx is already in the Y space. Okay, if it's 0, then the thing will be trivial. But if it's non-zero, then by the Hambana Theorem, there exists some continuous linear mapping such that the norm of F is equal to 1, right? And also I map the Tx, because this Y is, the F is in Y star, and this thing is in Y, so this will be equal to the norm of Tx. Okay? We know that this is true. There exists some F such that this is true. And from here, we can see, well, look at the Tx norm. This is equal to the F of Tx, right? And according to our definition for adjoint operator, it's just T star of F applied to X. and this is bounded by the T star of F applied to the norm of X. And this is also bounded by the operator norm of this T star, joint operator, in the F times the norm of X. Okay, and now remember that this F was chosen such that this is equal to 1, so that's just equal to this. And this also means that the norm of T is bounded about by the norm of the adjoint operator. And combining with the thing we have here, the two together means that the T is just equal to the T star, norm of T star, and that is just that. Okay? So that means the norm is kept. We consider mapping X star as a mapping from any bounded linear operator T to its adjoint operator T star. The norm is kept. Okay? So this is the isomorphic. So this mapping from this space to this space is an isomorphic, isometric isomorphism. Okay. Now let's look at. Well, since we can do this, we can consider like the bidual as we did before, or the adjoint operator of the adjoint of adjoint. So in this case, let's say that the adjoint operator T double star, and it should be interpreted as the T star of star, the adjoint of the adjoint. Okay, so if T star, because the T star is mapping from the Y star to X star, so T is from X to Y, then T star is from here, then T double star should be from the X star then star, so the bidual to this. Okay. Now, what is this? What is the relation between the T and this T double star? Right, that will be something very interesting. So in general, these two should be different in the sense that this are two different mappings, or they are living in two different spaces. Since X is just a subspace of X, the bidual, and Y is also a subspace of the bidual. So this T itself is more restrictive. Okay, and what we know is that if they agree, for example, if I'm looking at any element in the bidual, which is actually from here, we know that this can be continuous or it can be isometrically embedded into as a sublinear. This can be isometrically embedded into the one below as a closed linear subspace. So when we look at the T double star on the elements in that closed linear subspace, we'll see what happens. Okay, and to see this, let's say that we have this canonical embedding. So what this embedding is simply just mapping this X, as we said, as X to X double star using the evaluation. So this maps any X to just the JX. And that is how we define the UX. And similarly, I define V as this canonical mapping or canonical embedding. It's from Y to the JY, which is denoted by the VY. Okay. So in this case, we can work on the UX and VY. So what we can do is for any x in the space x, and also any y, so any f in the x star. What you can do is you look at the t double star, right? Because this is a mapping can be applied to the it's a mapping from the bidual of x to the bidual of y. So I need to apply to the bidual of x, and this ux is in the bidual. This one is in x double star. Okay, and then I know that when I apply this, I can apply this to something in. So after the mapping, this will be in y double star. So it can be applied to something in y star, which is what I have here. So that's why this makes sense, right? And then because the t double star is the adjoint of t star, so this is just the ux of t star f. Okay. Remember that this ux right now, again, it is in x double star, and this is in the let's say it's in x star, right? Because t star maps something here to here. Okay, so the f is in y star. So after the mapping, this is in x star. And this is canonical mapping. So this is just evaluation. So it's just evaluating this at the point x. Right? If you treat this as the jx of t star of f, it's just equal to the evaluation of this thing at x. Okay, so I can rewrite this as t star f at x. And again, because t star is the adjoint operator of t, so this is equal to f of tx. Okay, so another way to interpret this f of tx is that it's like I'm treating this tx, do a canonical mapping of that. So this v is mapping this something in y to y double star. So it's mapping this, so the v is applied to this, and it is in the y double star now. So it can be applied to f, which is in y double star. This thing is in y star. Okay, so this is what happens. So now we show that for any f and any x, so for any x in space x and any f in x star, this is true. This is equal to that. And this just means that these two are the same. Okay, these two are the same. So the t star, because the f is arbitrary, so this t double star of ux is just a v of x over v of tx. Okay. So now you can see this is in x double star, but it is just all this ux just form a closed linear subspace of x double star. Okay, and on the other hand, you can see that this t star right now, t star, originally it is mapping from x double star. Sorry, from x double star to y double star. Right, this is what we know. And right now, when we restrict our t double star to a closed linear subspace, which is the isometric embedding of the original x, it is equal to the v applied to the tx. But the v of tx, this is something, remember the tx here is in y. So the v of tx is just the canonical mapping to the y double star. The whole thing is just in y double star. Okay. So, so you can think this as, how should I say? the t originally is a mapping from x to y, so it maps any x to tx. Okay, and if we treat them as as in their biduals, like we treat this as in x double star, this is as in y star, then that coincides with the t double star right here. Okay, and on the other hand, we know that the t double star can be applied to not just the x to x. It can be also applied to the bidual, so which is larger than the original x. So you can think of this t double star is the extension of this t from, say, this is x double star, and this is the x. So it's a extension from the t originally only defined over this x, but now it is extended to the whole x, the whole bidual x double star, and that is our xt double star. Okay, and also we know that this norm is kept because we know that the t double star has the same norm as the adjoint operator of t, but this is also equal to the norm of t. Okay, so the norm is kept. So what do we know right now is like our extension theorem by using the Hambana Theorem, we have a linear subspace, which is x. This x is a linear subspace of x double star with the bidual. And we have a linear operator from x to y that is defined by this t. Then the x double star is extending that t to a mapping from x double star to y double star, which is this. So the t double star is like a extension of the t, and the norm is kept. Okay, so that's the relation between them. Okay, so now let's look at some examples. Okay, so this example involves convolutions. So let's think about a measurable space. Omega is the measurable space. Is a measure space. Mu is the measure, and I will ignore the sigma algebra of measurable sets, which are all the measurable sets that can be measured by this mu. Okay, it's a measure space, and also the k is a mapping from the omega to omega, and it's a square integrable. It's also measurable and square integrable. By that, what it means is that k is, I should say, the omega. It's not omega. I'm writing here. Is this? So that k of x and y square integrable means that you can do this in the dx or d mu x, d mu y, and this is the omega. This thing is finite. Okay. So that's what I mean. That's a square integrable. And now from here we can define this linear operator from. I'm going to show that this is actually linear. I'm going to show that this is a mapping from the L2 space to the L2 space. So any element in here, so if f is in here, just means that the integral of f d mu x, this is a finite. Okay, just means that, or this square is finite. Just means that. So I'm going to define this operator t by that. So for any vector u, any point u in this space, it will be mapped to the t of u, which is also a square integrable function. And that definition is the TU, since it's also defined over omega, so when you apply any x to omega, any x in omega, so this x is in omega, this is equal to this, or this is defined by the k of x minus y, or just kxy, uy d mu y omega. So you take the integral over y, and then you have the x left. For every fixed x, you can do this. Right? For any fixed x in omega, and for any u in L square omega u. Okay. Now I'll try to show that it's linear. This T is a linear bounded linear operator. So it's linear. That's pretty clear, right? So the T, just need to show the T of U1, so alpha 1 U1 plus alpha 2 U2 is equal to alpha 1 TU1 plus alpha 2 TU2. That's the only thing we need to know, right? Easy to show that by using the linearity of integrals. But I also need to want to show that this is a bounded operator. To show this bounded, I need to show that the T of U, the norm of T of U, this is the two norm. This, by definition, is the TU x square d mu x. I need to show that, or take the square root, but I have to take a square here. So I want to show that this is finite, or this is bounded by some constant times the u square, because I have square on the left. Okay, I want to show something like this. Well, let's see if that's the case. By definition, the TUX is the one above, the one here. So let's take the integral of kxy uy, sorry, dy or d mu y, then d mu x. I want to see that if this is bounded by something like that. Okay, so for the inside here, I can apply the Cauchy-Schwarz inequality. For any fixed x, these are two functions of y. And I can apply Cauchy-Schwarz inequality, this becomes less than or equal to the integral of kxy square d mu y, and also the integral of uy square d mu y, right? And then I have a square root, but I have this square outside, so the square root is cancelled. So I have this inside as my integral. So this is less than or equal to the integral of this kxy square d mu y, and then integral of uy square d mu y, right? This thing times d mu x. And now this is independent of x, so I can pull it out, it's just a constant, and that is equal to the square norm of u, square norm of u. And the rest is this, is this integral d mu y with that, and also another d mu x. And that is, according to our Davis assumption here, it is square integrable. Sorry, this should be square integrable. What am I doing here? Square integrable. So that's why it's bounded by the kxy square d mu y d mu x. And I know that this thing is going to be finite. It's a constant, and this. So this is like our C here. Okay, so it's indeed a bounded linear functional. Okay, so it's a bounded linear functional. Okay, so now let's think about the adjoint operator of this T. So I have this T here. What is our adjoint operator? So the adjoint operator, I'm going to claim it to be this. It's just a switching the y and x. Okay. Question, what? Is the adjoint operator of T right here? And the answer is the T star, which is, so the T is the mapping from this to, again, this square. So this is like the Rx, standard X. So T is like the linear mapping from X to itself. So the T star is supposed to be a mapping from X star to X star. Okay. But remember that X is equal to L2 and the X star is also equal to L2. This is actually equal to its own due. Okay. So the X star itself is also just L2 space. Okay, now I can apply this to any vector V, which is in L2 omega nu, or any point in L2 space. And then this is, I'm going to show this is also L2, and it can be applied to any x, and the definition is just the T star is just mapping V to this. The same thing as before, except that the x and y are switched, and then you have the V of y and d mu y. Okay, just switching x and y. Okay, so we're going to claim this. And to show this claim, we just need to see if this verifies the property of the adjoint operator, or the definition of adjoint operator. So remember that this can be applied to, how should I say, according to our definition, the T star V U should be equal to the V of TU, right? The question is, can we show this? Okay, the question is, can we show this? Well, so on the right hand side, this is equal to, according to our definition, this is just equal to the Vx times the Tu x d mu x, right? That's the definition for right hand side. Take the apply V to the T of U. But by definition, this is just equal to the, let me write it out. The Tu, we show that is integral of k x y u y d mu x. Okay, and then the d mu. So I should say use d mu y here, mu x. Okay, that's how I replaced, just substitute that as its definition. And then from here, we hope that we can exchange the order of integration. Suppose we can do that. Let me just keep this as a question right now. If this exchanging the integration is working, then I will do the integration with respect to x first. So that will give me the integration of, so this is the uy will be outside, integral of this k x y vx d mu x, and then the d mu y. Okay, and then we can just switch the notation of x and y. It doesn't matter, right? Switch the notation, then we'll have ux omega the k y x v y d mu y, and then the d mu x. Okay, so for any v and u in the L2 omega Lebesgue space, the square integrable space of square integrable functions, we have this. And this is like the integral of this k yx vy d mu y as a function of x. So I can maybe write it in this way. Think of this as a function of x. And then you have another function of x, which is ux, which is u. It's like a function of x. So it's like that. Okay, so we show that this is true. Well, if this actually works, if I check this one, then we just have from here to here. And this just means that this gives me the adjoint operator, which is t star of v, and that is what we claim. Okay, and that is what we claim. So as you can see, to verify that this is indeed true, we just need to check this. Okay, to show this one here, we just need to use the Forbidden Theorem. But the Forbidden Theorem just tells that if you can show that this is the integrable function, I mean the integral of this is finite, then it's done. Okay, so we need to use the Forbidden apply if we want to invoke a Forbidden Theorem to show this this equation actually holds. We just need to show that taking the integral, we get a finite number. Okay. Well, to show this, let's see. We just mixed all the integrals. That's just equal to the integral this kxy uy vx d mu x d mu y. Okay, and this apparently is less than or equal to taking the absolute value of the integrand, which is the kxy uy vx d mu x d mu y. Okay, and then we can put this as one thing, this as another thing. So we use the Cauchy-Schwarz. They're just giving me the kxy square d mu x d mu y, this thing 1/2, and then the other one also the integral of uy square vx square d mu x d mu y, and then 1/2. But remember on the right hand side, the second term right here, the u and v are separated. So you can do this for the dy and this for the dx. So this actually is equal to, this thing here is actually equal to the integral of uy square d mu y and integral of vx square d mu x. Okay, and then you have outside you have square root. So this whole thing here is with the square root is just the u norm times the v norm, okay, in the L2 space. And this is something finite. Okay, so the whole thing is just finite. And that by Forbidden Theorem, this is actually, this identity and this equality actually holds. And that completes the proof. Okay, this shows that the adjoint of the T is just mapping, it's just a mapping like that. Okay, just a mapping like this. Okay, so so that's one example, and we can also extend this a little bit to some convolution that we've seen. So this is actually even more general than convolution. This convolution is nothing but the kernel is k is just x minus y. And then we have the x kernel k is k of x and y. So can be easily attended to the convolution case. But in those cases, we want to be more specific. We want to do calculations. So the first First of all, you give a lemma of the Young's inequality. So this is another Young's inequality, same person, but it is more specific to this application right here. So we have, say, the P is in 1, it could be positive infinity, let's see. Okay. Let's say we have the P, which is from 1 to positive infinity. It could be even 1 or and infinity. And the F is in LP. The K is in L1. Then what we can claim is we take a convolution of K and F. Its P norm is going to be bounded by the 1 norm of K times the P norm of F. Okay, so we're going to prove this. The case 1 is that the P is strictly greater than 1, but not infinite. So in this case, let's look at let's first look at this quantity here. So this is kx minus y f of y dy. So you know this is just a k star of f applied to x. Okay, just convolution of k and f, which is this one here. Okay, I'm going to show, take the absolute value. I'm going to show how it is bounded. Well, this is less than or equal to integral absolute value of the integrand, which is this. Right? And now let's split the power for the k. I'm going to split it into 1 over p and 1 over q, because 1 over p plus 1 over q is equal to 1, where q is the conjugate of p. So this is equal to k x minus y to the power 1 over q, then k of x minus y to the power 1 over p, f of y dy. So I'm going to put this as a self with this self and these two together. And then I can apply the Holder's inequality. Holder's inequality tells me that I can put the q's power on the first. So I'm going to get of this kx minus y to the power 1 over q, then to the power q, and then outside, so this q and 1 over q will cancel, have the dy will cancel, and then I have another 1 over q outside. And the second one is I'm going to put a power k of x minus y, k a pth power on that. So I'm going to get this times f of y to the power p. And then again dy, and everything outside I have the p, 1 over p. Okay, I'll get this by Holder's inequality. Okay, so what this is, for any fixed x, I'm ranging all the y's from negative to infinity to positive infinity. So this whole thing here is just the 1 norm of k to the power 1 over q. Okay, and the second term doesn't change. This term doesn't change, but that's my estimate for this term, for this one here, and that's going to be my integrand for this p norm. So let's see what that is. Well, let's look at the p norm of the p's power of the p norm of the convolution. This is by definition is equal to the k star f of x to the power p d dx, right? And what we showed above is the integrand is bounded by this quantity here. So I'm just copying it. So it's k1 over q times this quantity right here dy. This whole thing to the power p dx. Okay. So what happens to this is, sorry, I shouldn't have this p anymore. I should say in this way. This thing has 1 over p's power, right? That's what we have right here. Okay, we'll have that. And then when I apply the p's power inside, I will have the k1 norm. I have the p applied to that as the p over q. And then again, integral of this kx minus y f of y to the power p dy dx. So now this is a constant that I can move it out. And then let me first move this out, p over q. And then I have the integral. I can definitely take the integral with respect to x first, right? So that's why I have this kx minus y dx. And then this thing together times f y p dy. But now after I take the integral with respect to x, from negative infinity to positive infinity, this is just the 1 norm of k. And the rest is just the pth power of the p norm of f. So now I have this k, 1 norm of k, and p over q plus 1 times the f p's norm, p's power of the p norm of f. But remember the p over q plus 1, this is equal to p times 1 over q plus 1 over p. But this is equal to 1. So this whole thing is just equal to p. So here this thing is just equal to p. Okay, so that's how I take the piece root on both sides. We will see that, sorry, this should be less than. Piece root of both sides, we will see that the claim holds. Right, this claim holds, or this inequality holds. Okay, so now this is for the first case. The second case, p is infinity. Okay, so in this case, we want to show that this thing is bounded by this times this, right? Because right now f is in our infinity space. Okay, so this is essentially just try to show that the norm, we just need to show that for any x, we want to check the k star f at the point x. We want to show that it's bounded by the right side, right? And this is, by definition, is just the convolution of the kx minus y f of y dy. And as you can see, this is bounded by the infinity norm of f, essential upper bound of f, right? So all the points are less than or equal to this. Function value f of y is less than or equal to this for almost all, almost everywhere, for almost all the y's. Less than or equal to this times the absolute value of that dy, from negative infinity to positive infinity. And this thing again here is this. So we show that for almost every x, this is bounded by that. So that's why this is true. Okay, so that's the second case. The third case is p is equal to 1. So in this case, we want to show that this 1 norm is less than or equal to k1 f infinity. sorry, f1. Okay, so now the left-hand side is equal to k star f of x dx. And let me just write out this convolution, which is just kx minus y f of y dy dx, and I can move the absolute value inside. So it's a kx minus y f of y dy dx. Okay, now it's the same trick as before. We can take the integration with respect to y first. Everything is integrand is totally positive, so we can exchange the integration, the order of the integration. So we do this integration of x first, then dy. But this part here is giving us the 1 norm of k, and then what is left is just the 1 norm of f. So it's equal to 1 norm of k times 1 norm of f. Okay, and that is exactly what we want to show, because the left-hand side is equal to that, and that is bounded about by the right-hand side.